Okay, this little mini lecture is about errors in prediction. Um, we need to interpret errors as deviations of the observed points from the regression line. So remember, this here represents the regression line, and all of these observed points deviate from that line. Okay? These deviations are called error terms. Okay? So expressed, this is error equals the observed value of y subtracted from the predicted value of y. These are all observed values, okay? And these are all predicted values. So if I have this observed score here of 48, okay, this is 48 on the y-axis, okay, what I predict based on the regression line is 38. Okay? This is what I predict a value to be when x is 8. Okay? So you can see that I'm off by about 10. Okay? And so in this case, this observed score has an error term of 10. This is called a disturbance in regression. Likewise here, when x equals 6, I'm underpredicting y. So I predict y to be 32. Okay? What I actually observe is 26. And this is a difference of -6. So my observed score, okay, has a residual or an error term of -6. Now, this section corresponds to section 11.3 in your textbook. And what I want to do is, remember, get an overall idea of error. We just went through, for example, how to solve for the error term for a single score. But what I want eventually is what we're going to call a sums of squares for error, in which I talk about how much the points vary from the mean overall, or not from the mean, excuse me, from the regression line. So back here, I can see that this is the regression line, and then I have individual scores that vary. If I want to know the sum of squares for error, I want to look at all of these points together and come up with one number that tells me on average how far are those points from the regression line. And that's what the sums of squares for error will do. Once I have the sums of squares for error, the only other part of the regression equation is the sums of squares for regression. And if I have the sums of squares total, which refers to the sum of the squared deviations of y from their mean, then I can solve for sums of squares for regression. So essentially I have my total variation, or my total sums of squares. If I subtract error from that, then I have the sums of squares for the regression. Now, remembering that prediction errors refer to the difference of the observed points from the regression line, I want to kind of start to introduce the idea of the proportionate reduction in error. The ability of any regression line to make predictions can be expressed in the proportionate reduction of error. And once we have these terms here that we've just gone through, the sums of squares for error, the sums of squares total, and the sums of squares for regression, I can solve for the proportionate reduction of error by subtracting the error term from the total and dividing by the total. The proportionate reduction in error tells us how much of my variability in y can be explained with knowledge of x. And so that's a very powerful statistic. And this is detailed in terms of exactly how to make the calculations. It's not complicated. It's about computing deviation scores, these deviation scores in particular, what I observe from the mean of y. And again, section 11.3 goes over that very well.